Thank you, Megan and Diego, for organizing this wonderful school. Let me first be sure that even if I'm not next to these mics, you can hear me in the back. Can you hear me? All right, thank you. So, a few words about, I like to be interrupted when I lecture. I know this is not at all a European thing. And I doubt there are many American PhD students here. Anybody? Huh? From good old USA now, right? So I hope so. I remember that I spent a whole sabbatical in France, and one of the things I did was to teach a course, and I had to beg the students, I don't know if you understand. You have to let me know somehow. If you're not going to raise your hand to ask questions, how would I know? At least, you know, try to have anything else but a poker face expression. Anyway, so yes, please do interrupt me. Let me worry about whether I'm going to answer on the spot or in a moment, but I really would like to make this as interactive as possible. Now about the subject matter. So the story of provenance is in the general picture of database theory is a relatively new one, although of course for considering the age of the audience, the dominant age of the audience, it's a very old story. I mean, for me, I'm at the end of my career and most of you are at the beginning of your careers. And I feel a little emotional about that, sort of like passing the baton. But I would like to you know, tell you about the story, and hopefully some of you might be interested in using it in your research or continuing the research on this topic. So it's the story of data provenance. Specifically, from the perspective of databases. And in fact, since I'm giving essentially two lectures, the main difference being that one is in PowerPoint and the second one is in Beamer. It is also a story that, that looks at the problem from a logical perspective. So I'll tell you more details as we go along. Aside from that, I want to apologize to my old friends who are here, who are going to be bored to death, so you can just leave now if you want, unless it's more comfortable to sit here and work on your presentations while I speak, which I understand. All right, so what is data provenance, which is the topic of our morning? So for many researchers and practitioners in databases, just and in systems and computer systems, just tracking data provenance simply means keeping a log of some events that happened. From a database perspective, it could be, and one of these events could be the use of a particular relation in a database, or a particular tuple, or some other data structure, depending on your data model. But it turns out that while this is satisfactory for a whole bunch of applications, a new, which I would call essentially declarative approach to data provenance was pioneered by somebody I am very happy and proud to call a friend, Peter Bühnemann. I think I should have changed the 15 plus, because that's an old slide. So I think Peter's work was 2001, so that's like 20. And that allowed us actually to understand the problem of data provenance in a more compositional and generalizable fashion. And that also allowed us to be more ambitious about what to do with provenance, including what many of us call provenance analysis, that is using data provenance to derive more complicated properties of data. So what is this declarative perspective? Well, at a sort of general BS level, you got an input which is a structured collection of data, let's call them items. And you have a high level structured computation, which could be, well, it could be, of course, SQL, but it could be any kind of related high level language of transformations, and produces an output of similar items. And then what are some examples of this kind of what I mean by structured computation? Well, we have database queries, but also something more complicated like schema mappings. People have looked at scientific workflows, more or less formalized, data-centric business processes, network packet routing captured by some kind of data log, even static analysis of software processes captured also by some kind of data log, and even logical model checking, as you will see in my second lecture today, and the associated games. And so in this context, provenance, loosely speaking, means that you capture how an item in the output depends on maybe not all, but various items in the input. And once you have captured this in a precise manner, you'd like to use it for analysis. And I mentioned here two classes of analysis that you can do with provenance. One are causal analysis. So consider an output item, and you can think of identifying what we call counterfactuals of the kind, well, if some input items change or disappear, is this particular output item, I don't even know what letter that is. Anybody can help me? It's var sigma or sigma, yeah. I have no idea what I put there. Anyway, so consider an output item sigma. So the idea is, what happens to sigma? Does it change? Maybe it disappears from the output. So this is one kind of analysis, and you can use that for propagating deletions from input to output, and for diagnostics of wrong answers. You should go backwards. Then there is binary trust. If you trust certain items in the input, and those are the only ones you trust. More importantly, if you do not trust some of the items in the input, which items in the output can you trust? So call this binary trust. And even something perhaps surprising, access control, you can associate access control levels like things like public, confidential. I'll show you several examples. The kind of clearance that you need. So if you want to see a particular item in the output, do you have the clearance for it? Yes, so you can determine this if you know for which outputs, for which items in the input you have clearance for, okay? And you can also use this for probabilistic analysis. This is one of the topics that will be examined much more carefully. But provenance is a certain kind of provenance is one piece of understanding probabilistic databases, as you will hear from Antoine tomorrow. Another kind, and that's even more interesting, is that you can do certain quantitative analysis. Again, you consider an output item. Again, Now, what you do about the input items is you can assign a price to them. Okay, so you just say it costs you so much to get this part of the input, some other parts of the input are cheaper. There's an entire line of work there about data pricing and so on. And it has been significantly pushed forward by Paris Koutris. And given that price of the input items, what can you say about the price of a particular output item? Another application is compute confidence scores. So this is also trust, but it's not binary. You're not just looking to trust or not trust. You're looking to find a degree of trust. You assign a confidence score to each input item, and then you compute the confidence score that you consequently have in the output. This will be immediately illustrated with a simple example. Before I do that, I want to spend a moment on the word provenance, because perhaps many of you have encountered two other variations of it used in computer science: pedigree and lineage. So, okay, so the Oxford English Dictionary says that provenance is the fact of coming from some particular source or quarter. I don't know how helpful that is. Origin, derivation. So Ian Peter Buneman makes the following quip. You should know that especially data scientists in biological sciences are quite enamored of using pedigree instead of provenance for and then of course you probably know that many databases, especially on the system, the people on the system side prefer to use lineage. I'll have a word about that in a moment. And so Peter said, well, you know, pedigree is for dogs or horses, lineage is for kings, and provenance is for art. So our choice should be obvious. Okay, so anyway, I think that provenance there was a time 20 years ago when using provenance for what I call it, provenance, was a little not so common, but now it's more common. Here's an example that that should quickly anchor us in reality. So suppose that you have some people with data. Okay, so this is a bit of a joke example. These are two of my colleagues. Sue is Susan Davidson and Zach is Zach Ives, both database people. So let's say that Sue and Val are noted zoologists, and they have information about what kind of animal. So Sue has information that cats eat mice and rats, and Val has information that rats are gray and mice are gray and red. Okay, so that's a problem. The idea is provenance is going to help us identify questionable information. Okay, so these are my field notes and Susan's, and computational zoologist Zach writes a query or a transformation that takes this data and produces an output that talks about the color of the food that animals eat. So Zach concludes that cats eat both gray stuff and red stuff. Okay, so now of course in binary trust you can simply say for each piece of information whether you trust it or not. And you know, Sue is a very reliable zoologist, and so we trust both her items. And Val is a somewhat unreliable zoologist. So we trust that mice are gray, but we don't trust that mice are red. And rats are gray. And then you would like to conclude, of course, that if you are to trust Zach's data, and Zach does not have the original data, just computed from the original data of Sue and Val, if you want to trust Zach's data, you can trust that cats eat gray stuff, but you cannot trust that cats eat red stuff. Okay. Now, even more complicated is that maybe questionable methods were used by Val even in determining everything about mice. So Val's data about mice is highly unreliable. So then we're not going to trust even that mice are gray. How does this change propagate to trusting the output items? Notice that we still should be able to infer that cats eat gray stuff, even though we have changed something in the input. That's because of the rats, obviously. Okay? Here's another possible application that, yes? Def, you know. So binary trust just means trust or no trust, yes or no. But quantitative trust or degree of confidence is something we can do as well. I'll explain in a moment. Yes, so I'll actually show you that we can also propagate some numbers. Okay. All right, so I'm sorry I didn't see you. I made a big fuss at the beginning that I want to see your questions and so on. Yes. So this task is coming. Who is giving it? So who is annotating? Yeah, well, so everything about the input is a domain-specific activity, which is annotated by experts and so on. The only thing that that the provenance work does for you is to show how to propagate those annotations about the input into annotations about the output. And given that nowadays biology especially is very much a data science, it's very common that people actually have pipelines of transformations like this simple example. They start with multiple databases that were annotated by experts and produce databases completely, as it were, automatically. And you'd like to see how those annotations propagate. Okay? Okay, so with access control, suppose that Susan's data is public, that's pub, but Val's data has different degrees of access control. Val's very cagey about his data. So, you know, when biologists say, well, I'm not going to share my data with anybody, maybe it's because their data is not that good, huh? So Val makes the fact that mice are gray and red top secret information, and rats are gray, that keeps it confidential. And the question is, now, as a computational scientist, Zach transforms all this data, presumably having access to everything. But if you want to allow a user to look at a user who looks at the output of Zach's data, of Zach's transformation, that user should have some clearance for accessing the input data in order to see which part of the output data they have clearance for. So what is that clearance? That's what provenance will help you do. So it turns out that cats eating gray stuff is confidential, but cats eating red stuff is top secret. And here is confidence scores. Yes, sir. I'm just making this up. Well, it should be, okay, so the information that you use to derive that cats eat gray stuff is jointly using the fact that cats eat rats and rats eat gray, rats are gray. So when you use information jointly, for example, in the case of access control, you should actually use the higher level of access control. When you use information alternatively, you should use the lower level of access control. But what does it mean, all this alternative and jointly? That's what the provenance framework does for you. Yes? Inconsistency, no. So, I mean, consistency should be, it's not in many works in databases, but consistency should be a logical concept. Yes? So what you declare to be consistent or inconsistent logically, and the way it propagates, you should have some sort of logical theory about how that propagation goes. And provenance can allow you to do that. What I'm showing here are simply annotations. So the process of the computation also can transform the annotations according to laws that I will show you in a moment, but not necessarily call them consistent or inconsistent. Okay, so now let's not worry about how to see this work in the context of inconsistent information. There'll be a lot more about that by other people here. Okay, so the confidence scores, remember you said, well, I mean, how much do you just trust or not trust? Well, suppose that some experts think that Susan's data, each item is, they have confidence 0.9. So I'm using numbers between 0 and 1. You're going to say, are these probabilities? Leave that for a bit later. But of course, same experts are highly dubious about Val's data about mice. So they only have confidence 0.6 in mice are gray and 0.1 in mice are red, and so on. So how does this propagate to the confidence we can have in the output items? Boom, some numbers. How do I come up with these numbers? Okay, so I'm going to show you the computation, but I will have to justify it in the semiring framework. So the computation is the following. You use multiplication when the information is used jointly, and you use maximum when the information is alternative. The example here that we have, for which we have alternative information, is the fact that cats eat gray food. We have two different ways of inferring that cats eat gray food, correct? One because they eat mice, which are gray. The other one because they eat rats, which are gray. And we take the maximum of the confidence because it's enough for, if we're highly confident that that rats are gray, don't worry about whether mice are gray or not. You can still determine that cats eat gray food. Okay? Yes? Because you're thinking probabilities, right? So you're thinking that you multiply these things, and because they are numbers between 0 and 1, they must be probabilities. So I may be assuming independence, maybe. But this is a framework that is not probabilistic at this level. I will show you in a moment the semiring in which these calculations happen. Although there is a certain interpretation in hidden Markov models in which, yes, there is independence assumed. So in hidden Markov models, we can use these kind of calculations to derive what's called the most probable explanation. Okay.
Do we also consider like the information from different sources to give assigned weights to them? For example, Sue is an expert, and she have more like confidence than Val isn't.
You mean if there are annotations by different experts, and how do I combine them on the input?
Yeah.
So I suppose I could take the following approach. I can consider let's say we have two experts. I can consider their information to be alternatives. I can also consider it to be joint. That's not part of the computation. There's something that you do prior to assessing how the information propagates through the computation. It fits in the framework, but the decision whether to consider the two experts alternatives or jointly is outside the computation. It's something that it's a qualitative domain-specific decision. Okay, so you can even do data pricing. I think you by now got the idea, so I'm just going to quickly show you that. Well, so if you pay $10 for Sue's data, but only $6 for Val's data, $1 for the information that mice are read, etc., you can calculate how much you should pay for the output items. That's also something that provenance tells you. How the price propagates through the computation. Okay. So I did it, 3-4 times? Applications having to do with binary trust, deletion propagation, data access control, data pricing. Question is, should I do it every time in terms of a specific domain? I don't have to, because I can do it generally in terms of provenance, abstractly captured, and then I can evaluate this abstract provenance in the different examples of applications I showed you. And that's the core of the work I am telling you here about. You do it once abstractly, and then you use it repeatedly. So instead of labeling the input items with actual numbers or prices or whatever, we're just going to label them with some abstract, call them provenance tokens, which are just labels that label distinctly, if you want, different items. And then what provenance tracking means is to propagate these tokens through the computation. As they propagate through the computation, they become from just simple symbols, they become expressions. How do they become expressions? I'm about to explain. Well, the two rules for understanding these expressions are the following. Analysis of how we use this data so far tracks two distinct ways of using it. One is if they use the information jointly. From a database perspective, these are things like Cartesian product or join. Yeah. And if you do that, it's one kind of provenance propagation. Another one is you can use the information alternatively. This happens, for instance, when you union sets of items, or when you do projections on relations. Because when you do projections on relations, you may end up with the same tuple obtained from different tuples in the input. You erase the part that distinguished them. Okay? And we have developed this framework that is input-output compositional and modular. so that we can construct these provenance expressions, and then later we want to evaluate them to obtain all this information. I showed you binary trust, access control, confidence scores, data prices. Okay, so now we're going to be a bit more abstract, and what jointly and alternative means is going to be represented by two abstract binary operations. So suppose we have a set of provenance tokens, and we don't know exactly what it looks like, but suppose we have a space of general annotations of information that, let's say, are expressions in these tokens. We call that prov of x. And let's define a prov of x relation. It's a relation in which every tuple is annotated with some element from this space of expressions. Now, I can say that I have two binary operations on this space. Multiplication, so I'm going to use this is not actual multiplication, and it's not actual addition because these are not numbers. But as usual in mathematics, we abuse the notation. And I'm going to use the multiplication symbol and the addition symbol. As long as everybody understands that these are abstract operations, just denotated this way. So times and plus. And then we're going to have some special annotations, which are going to be 0 and 1. So you're going to wonder, why do I need to annotate tuples that are not there? Well, I may not need to annotate it in the beginning, but then I may want to do experiments in which some tuples are deleted. And the annotation of a tuple that gets deleted, we're going to call it 0. Okay? Another even more interesting annotation is I choose to annotate, I have to annotate every tuple, and I choose to look at a tuple as something that's always available. I don't care, maximum trust, 0 price, it's always there. I don't care to track it. That's also very useful, and we can annotate it with something that we call 1, like a neutral annotation. Yes? Oh, yeah, don't worry. I know that join can be expressed using Cartesian product. Just I'm trying to reach different parts of the audience. Okay, so, all right. So now this space of provenance expressions has two binary operations and two constants, 0 and 1. Now, we're going to follow the usual game that we play in databases, and we're going to define an algebra. Now, except that this algebra is not going to be on plain relations, but on annotated relations. And I'm going to call it K-relational algebra, where a K relation is a relation annotated with elements from K, which is an even more abstract thing than provenance of X, which will actually capture both the expressions for provenance and their applications, like those numbers for confidence, like the trust values. So more generally, I'm looking at K plus times 0 and 1. And what is a K relation? Well, annotation is a function. So I'm not careful here about the arity of the relations. You can work this out. A relation is now a function that associates to every tuple an element from the space K of annotations. And the question is, what should the space K of annotations structure be? So one of the things is, because relations are finite, one of the things that you can say, well, maybe I'm considering an infinite domain, so I may have infinitely many tuples, but I'm going to assume that except for finitely many, the others are absent. Okay, so R of t is 0 for all but finitely many t's. So take the positive relational algebra, which means select, project, join, union, for example, and generalize it to a K relational algebra. And here is how we generalize it. I'm just going to show you two clauses. Union, you add. Cartesian product, you multiply. It's messier for join, for select, project, and so on, but you can figure that out. Now, I will actually I have in this particular talk some references to a bibliography that is not in my talk, but will be provided together with the slides of this on the website that you guys are organizing. So don't worry about references and so on. Everybody will be able to follow up. If you get interested, you can see exactly how this is generalized to every select, project, join, union operation. So now you see what plus and times is. 0 is used for selection and projection, and it's used for select. 0 and 1 are used for selection, and for projection we use plus. Okay. Now, if I choose to make this K relational algebra as similar to the positive relational algebra as I want, then there should be some equivalences that should be satisfied. I don't have a list of those equivalences, but you have learned about them because they are used in every relational optimizer. Okay? So keep them in mind, and with that, there's a simple proposition that those desired optimization equivalences, when required of the K relational algebra, hold exactly when the space of annotations is what's called by algebraists a commutative semiring. And I'm going to show you exactly what that is in a moment. So this generalizes positive relational algebra, or equivalently unions of conjunctive queries, or equivalently non-recursive data log. And you should know that particular examples of such commutative semirings are already implicit in what we learn about databases. For example, set semantics for databases corresponds to the semiring in which, so B is the set true false, and plus is or on booleans, times is and then bottom and top there that you see they are false and true. For bag semantics, there is another semiring, the natural numbers. Plus is plus, times is times, 0 is 0, and 1 is 1. Isn't that great? If you are familiar with the work on incomplete databases of Imielinski and Lipski, then you have another semiring for some kind of conditional tables, but without variables inside the table, for those who know. So they're called C tables. And there, the Boolean expression is the annotation. And again, you have disjunction, conjunction, but now at the level of expressions, you have false and true. Yes? I mean things like projection and selection can be pushed inside joins, and all these other equivalences. If you go to the Bible, which is the Alice book, which is Abiteboul, Viano, and huh? Yeah. You will see in one of the chapters is a whole list. Okay. Yes. Senior moment. All right. So, and there's another semiring I wanted to mention. You can consider a semiring of subsets of some finite probability space with union intersection and the empty set and the whole set. And these are actually have been used for the early work on probabilistic databases. They call them event tables by Zimany and Für and Roleke. Okay. So what is a commutative semiring? So we have K is a domain of values for the universe of the structure. Addition must be associative commutative, 0 must be an identity for that. Multiplication associative, 1 is an identity. As usual, multiplication distributes over plus. As usual, 0 is what's called a, whatever it is called, A times 0 is equal to 0 times A is equal to 0. And moreover, multiplication is commutative. So this looks like what you may have learned as a commutative ring, except there is no subtraction, okay? All right. So now let's do the same calculations we did before, but abstractly. So instead of annotating the inputs with numbers or various values and so on, let's annotate them with tokens. So these P and Q are the tokens, P and Q for Susan's nodes and RST for Val's nodes. And then the calculation is, depending on how this computation is expressed, produces the annotations that you see there. Let me highlight them. Here they are. Okay. Which are expressions in terms of those provenance items and in terms of the operations of some semiring, plus and times. What is the computation here? The computation is very simple. It's a join of those two tables. I expressed it in conjunctive query notation there. So Zach's table is a join of Sue's table and Val's table. Okay? Yes? So when what you're looking for is the minus, which exists in rings, but not in semirings. So what we have here on the addition structure part is actually a monoid. We don't have a group. That's a problematic in general. That's an issue that I will address at the end because it's one of the issues that has been attempted. Solutions have been given in various ways and they're not all of them are perfectly satisfactory. But might it make sense? Well, it depends. What is the inverse? From the database perspective, what does it mean to have a minus? Well, there is difference of relations, yes? So that doesn't necessarily mean a group. So by keeping the set of tokens as abstract, the diagnosis for wrong answers, deletion, propagation can be done very easily. So notice, if I set R equal S equals 0 in those, let me erase my Yes, I made here. If I set r equal s equals 0, p times r is becoming 0, and p times s is becoming 0, but q times t stays. So notice that I can actually see the effect of deleting from Val's table these tuples that are questionable. This tuple and this tuple. If I delete them from Val's table, you're right. I mean these ones, R and S. If I delete them from Val's table, the result is going to be that you just keep the tuple cat eats gray food. And the other tuple, p times s, is going to have a provenance of 0, so it's going to be absent. All right. So here is a notation for these expressions. We call them Provenance Polynomials. And why do they look like polynomials? That's a great thing about semirings. Their operations as their algebraic identities allow you to put any expression involving plus, times, and so on into polynomial form. The polynomials here are only are simple. The first one only has two monomials, PR and QT. But in general, you may have natural number coefficients, and in general, you may have exponents which are 1, 2, whatever, 3. So what do they look like? What are the properties of these provenance polynomials? So we propose them as an abstract way of storing provenance, of expressing provenance. They have the nice property that the commutative semiring of the polynomials is freely generated. I'll show you this property, how to use this property in a moment. It's called algebraics call it a universality property involving homomorphisms. And provenance polynomials are computable in polynomial time, data complexity. And in practice, I just have to, at this point, people ask, oh, these things are gigantic. And they can be if you implement them badly. But when we developed this framework in 2007, 8, 9, TJ Green and Greg Karvounarakis and Nick Taylor actually developed, under the lead of my colleague Zach Ives, an implementation of this notion of provenance in the system called Orchestra. And it turns out that using cleverly graph representations and so on, the provenance information only adds about 30% overhead to the databases. And what they used was actually an off-the-shelf Oracle implementation. So you definitely do not store them as polynomials in polynomial form, because that's, I mean, the size is still polynomial, but it's exploding in practice. So instead, we store a graph representation that essentially makes use of common subexpressions, because we are computing the provenance not just of one tuple, but the provenance of all the tuples in the answer of a query. And when you compute the provenance of all the tuples in the answer of a query, there are a lot of common sub-expressions. Okay. Yes. The what queries? Yeah, I will consistently mention them in a moment if I get around to them. Data log is my next topic. So we go there. Okay. Yeah. You should have said that I inconsistently don't mention it. That was an inconsistent. Yes. No, absolutely. So, I'm going to start going a little faster, but what I went on purpose slowly here because basically I want you to become interested in finding out more about this. So how do we read the polynomials from the provenance perspective? Suppose I have an output tuple that has provenance 2r squared plus rs. I told you these are literally polynomials that differ from the usual polynomials with integer coefficients. The difference is that they have natural number coefficients. So when we have 2r squared plus rs, that means that the tuple that has this annotation has 3 derivations in the computation that led to it. The 2 of the derivations are, which is an annotation of an input tuple, they use that tuple twice. There are 2 different derivations that each of them uses that tuple twice. So the exponents mean how many times you use a tuple, and the coefficients mean different derivations. And then, of course, there is also a third derivation that uses r and s once. So these polynomials capture the use of input data in the derivations of the output data. Yes? No. Why should they? This one apparently seems to, yeah. Yeah, but I mean, no, they don't have the same degree. You can, all kinds of things happen in a general positive relational algebra query that do not preserve that. So in addition to the provenance polynomials, we have therefore 2 kinds of semirings. One is provenance semirings, which are these polynomials. And I said I'm going to go a little faster now. We also developed other kind of polynomials, and sometimes we captured, using the semiring framework, work on provenance that was done before. Like, for example, this seminal work about Y provenance by Buneman, Kana, and Tan. This is called witness Y provenance. But we also have application semirings. So for instance, the access control application I showed you before has a set A of those access control values. The 2 operations plus and times are now min and max. Yeah, we'll see a bit more about this. We also have the Viterbi semiring for most probable explanation. So here we have all the values between 0 and 1. The plus is max, the times is times of probabilities, 0 and 1, and they are not probabilities, but they can be interpreted as probabilities. I should also say that I don't know much about it, but there is a work on possibilistic inconsistency that has even closer relationships with this. And then you have provenance specialization, which I'm going to exactly show you how it works out. you consider the provenance semirings. They are freely generated by the tokens in various ways. And you have a result, a fundamental result, that queries commute with semiring homomorphisms that looks like this. So when I say QL here, it's a general query language, and so far we only have one, the positive relational algebra, right? And then we have two semirings K1 and K2, and let's say we have a homomorphism between them. Then we have shown that this kind of diagram commutes for any semirings K1 and K2, and for a whole bunch of query languages. Of course, the positive relational algebra, but also data log, and I'll get to data log in a moment, and other extensions. Like I said, I will explain all these bibliographical references, other extensions to things like nested relational algebra, to things like XML, to things like even like data-centric processes and so on. There's a whole bunch of work that was done. And once you have the provenance, you can specialize it in any of the application semirings. And this is how it works. You begin with a function f that associates, to specialize provenance, you associate or interpret every provenance token as a value in a semiring A. That, because the semiring has a free universal property, lifts to homomorphism from prov of x to A. And if you plug it into the previous diagram, this commutes. So instead of actually having to directly compute the query on tuples annotated with the semiring A, you can do it on tuples annotated with provenance and then use the homomorphisms to interpret the values of the result. That's what this story says. And you can do things like number of derivations, multiplicity in the natural number semiring, confidence scores, access control levels. You can use also this to simplify provenance by, for example, mapping multiple provenance tokens into the same provenance token. You can just say, well, I'm not going to track every input tuple separately, but I'm going to track all of them together. Okay? So I mentioned some of these application semirings, the Viterbi semiring, the tropical semiring, which is actually isomorphic to the Viterbi semiring, and even fuzzy logic if you work on that. I'm going to skip this. It just illustrates what I showed before. So the analysis that was made, especially by T.J. Green, showed that various examples of provenance that were at the time developed in other work, for example, in trio, can also be seen as semirings. So here is a hierarchy of provenance semirings. Let's say that you have the following polynomial is an example of a provenance. This one does not, in this one, it's not the case that every monomial has the same degree. And actually, I can easily show you that for any given polynomial, I can come up with some relational algebra expression that produces that polynomial as an annotation. So you can interpret this in the, so if you compute the most general provenance in the semiring of polynomials, n of x that you have there, you can simplify it in two different ways and describe provenance in trio by dropping the exponents, and then by dropping the coefficients, you can describe Boolean provenance in which you do not count different numbers of derivations, how many different derivations, but whether there is a derivation or not. You can further drop the coefficients from trio or drop the exponents from that Boolean polynomials derivation, and you get what's called a y derivation. And so if you see here this y, xy plus xz, it tells you that there are three possible derivations of that item. One uses x and y, one uses just y, and one uses x and z. It doesn't say how many different times it uses each of the items. And it doesn't say if there are multiple derivations that use the same inputs. And the problem is that this cannot be used actually properly for trust. Instead, we have developed another example, absorptive polynomials. And in that one, we can deal with trust properly. There is also the semiring that is used in probabilistic databases. And that originally very diverse provenance, 2x squared, whatever at the very top. If you just keep it as a Boolean kind of lineage, as they call it, it just comes down to y plus xz. So my point is that that there is an entire hierarchy of provenance semirings in which the provenance is from most informative to least informative. The least informative is the one which of x that simply calculates who are the tuples that were used for derivation, not in what ways or why and so on. Okay. All right. Notice that in the various application semirings, like natural numbers, like the Viterbi and the tropical semiring, like the access control semiring, like the Boolean semiring, can be specialized. But if you choose a less informative way of recording provenance, then you can only specialize it in some of these situations. So for example, if you want to specialize all of them, then you choose n of x. If you want to specialize in, for instance, enough of them, you can choose the absorptive polynomials. There's another reason to do that, which I will comment in a moment. And then if you want to just do Boolean, which is essentially distributive lattice computations, you can choose post bool of x. Trouble is, if you use the original lineage approach, you cannot do any of these things. That's in the lower right corner. Okay. And here I have, the previous slide was called the hierarchy of provenance semirings, and this one is called the menagerie of, sorry about that. I think they were in different talks. So this is a whole list of how you can understand these provenance semirings. I don't want you to read it in detail, but you can also understand them in the following way. For example, the Y semiring consists of sets of witnesses, sets of alternative sets of witnesses. And if you use other things like trio, that's bags of sets, sets of bags, minimal sets of bags, etc. The most general one is bags of bags. So when I say bags of bags, I mean we actually track all the witnesses and how many times they are used and how many different ways of using those witnesses there are in different derivations. Okay, you have stopped asking questions, which is worrisome. Yes.
The previous slide
I'll go.
I was a bit lost in this hierarchy. So
yes, good point.
Like, do really these arrows come only from this operation?
So what do the arrows? What do the arrows mean? So I say this is more informative and less informative. The actual meaning of the arrow is at the bottom. When there is an arrow, there is a surjective semiring homomorphism, which preserves the tokens. So every time you go down one arrow, you maintain the structure of the semiring because it's a homomorphism, but it's also surjective, so you cover everything that's in the target. But you lose finer distinctions. And well, I think that showing how the coefficients and the exponents go away is one good way to understand what you lose. All right. Okay. Time for data log. Before I plunge into that, any more questions from the previous? Yes. Is it? Are they any use? There was one. Which one? Last line. This one. Okay, so these are polynomials with coefficients from natural numbers and with indeterminates from x. No, into this, no, because this is the free commutative semiring. So every, I mean, there could be others, but if there is another one that has, maybe even a surjective is enough. Yeah, if it has a surjective homomorphism, then they are isomorphic. So this is kind of, so the joke in some previous talk was that it's a semiring that rules all of them. Other questions? Yeah. Okay. So we already are have something for the to approach data log, which is that if you recall, the immediate consequence operator in a data log program is already expressible in positive relational algebra. Yes? We're talking for the moment just about data log. No, well, with set semantics and no negation. So here's an example. Can you tell that f of t is the immediate operator, the immediate consequence operator for a transitive closure program, which is the most, everybody exemplifies data log with transitive closure. In fact, somebody who's not in our field once told me, do you guys have anything else that you can compute with data log? Good point. Okay, so now I want to generalize this to the semiring framework. If I just consider, I can easily consider on the same k-relational algebra that I described before, the generalization of the immediate consequence operator, and I have a fixed point equation. So I can write the data log program as t is equal f of t. And if I have a solution to that, then I can say that's the semantics of data log on k-relational on k-relations. But of course, in order for that to happen, this is not the same story as in the case of sets. In the case of sets, you iterate this operator, And after finitely many steps, you have closure. Here, that's not the case. So anybody knows what's happening if you try to do data log on bags instead of sets? It's an old thing that has been forgotten. So actually, if you try to do data log on with bag semantics, you will find that certain tuples keep being derived infinitely many times. So you don't have what's called a closure ordinal. All of a sudden, it's not finite, but it's omega in general, right? Now you can still, there's a way out. So this was not much publicized, but I think Mumik and Shmueli and Mumik proved that in fact, you can decide whether a tuple, you can stop the iteration and detect whether a tuple is going to be derived infinitely many times. So you still have a kind of finite semantics for it, at least from a computational perspective. Well, in what we have here, we're trying to do something even more general. So it turns out that you can also consider the set of all possible derivation trees, and you can do a semiring sum over all of them. Not gonna get into details. But more intuitively, you can also introduce unknowns for the annotations of the IDB tuples, and I'll show you an example. And then instead of considering this more abstract fixed point, you can solve a system of fixed point equations over the semiring K. Equations in which the right-hand side, I think I will need batteries soon, just a moment. In which the right-hand side are polynomials whose indeterminates are actually these unknowns that you've introduced for the annotations of the IDB tuples. Now, I'm being pretty cavalier here, assuming that you know what I'm talking about when I talk about IDB and EDB. I think some of my colleagues who make presentations here will be a lot more careful about it. But stop me anytime and ask me. And in fact, I prefer to explain them on an example. Okay? So the analysis that we did in the original work was a PODS 2007. We found out that in order to have solutions for this, it suffices to consider what we call omega continuous semirings. What are those? Those are semirings such that the immediate consequence operator has a least fixed point on K relations. It's pretty clear that that's what you would like to do. So in order to talk about least fixed points, you need an order. So these semirings have an order. What is that order? Well, it turns out that this was a known concept. So a semiring is called naturally ordered when there is, so x is less than y, when there is a z that you add to x to get to y. So this natural order specializes, for example, for the Booleans, to the usual false is less than true. For the natural numbers, specializes to the usual order. Yes? So it's intuitively what you'd like to have. And you can go semiring by semiring and see that this makes perfect sense, this natural order. Now, in a general semiring, this relation is actually reflexive and transitive, but so it's a pre-order, but may not be antisymmetric. So we say that the semiring is natural ordered when the relation is also antisymmetric. Then, for a naturally ordered semiring, we say it is omega complete when it has least upper bounds of these omega chains, which is x0 less than x1 and so on. Soups of these. And finally, we say that the semiring is omega continuous if, moreover, these least upper bounds are preserved by plus and multiplication. So among our examples, the Booleans, the tropical semiring, the Viterbi, the access control, the fuzzy semiring are already omega continuous. This one is not, but you can make it omega continuous by putting a top of it. So you add an element, you call it infinity, you extend the operation. So for example, 3 plus infinity equals infinity, 5 times infinity equals infinity, and so on. And this one is an omega continuous semiring. And interestingly, for provenance, n of x, the semiring of polynomials, is not omega continuous, nor is a semiring of polynomials in which you allow the coefficients to be infinity omega continuous. Any guesses what's going to take to be omega continuous? Well, the polynomials are finite, yes?
You also need the exponent?
Actually, no, not here. But the polynomials are finite. And remember, I said that for bags, you may have infinitely many derivations. And these derivations need not necessarily have the same provenance. So if they have the same provenance as monomials, then their coefficient is going to be infinity. But what if you have a loop? Consider transitive closure. And if you have a loop, and every time you use the loop, you add one more exponent. You use the tuple that produces the loop, you use it 2 times, 3 times, so it's going to appear with all these exponents. So what used to be a finite polynomial now becomes an infinite polynomial. What's that? Well, it turns out that we mathematicians know this. It's called the formal power series. So formal power series form an omega continuous semiring. And here's an example. Okay, so that's too much theory. This is transitive closure done badly. Yes, it's not linear because I am joining T with T instead of with E. But it makes for a more interesting example. So the EDB predicate is E. These are the tuples A, B, A, C, C, B, 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 whatever. These are the tokens, MN and PRS. And now I'm considering the IDB predicate. And although I don't know a priori who are going to be the tuples in the IDB predicate, and it's a theorem that they're going to be exactly the ones that appear also in the set solution. I could compute that, or I could compute this incrementally as I iterate. So these are the tuples in the output. I just don't know their provenance. So let me associate unknowns. X, Y, Z, U, V, W. These are the unknown provenance of these tuples in the output. And then, just by instantiating the 2 data log rules with every possible valuation, you get a system of equations. So this system of equations is over a semiring in which the unknowns are this X, Y, Z, and the other, the MNP polynomials, they form a sort of environment semiring of polynomials over the input. And therefore, I can use them. So then you solve it. So these polynomials are exactly the provenance of the immediate consequence operator, which is in RA plus. And you solve it and boom. So XYZ is simple, but V is this infinite series, formal power series, whose coefficients are the Catalan numbers. So I'm calling this infinite sum SC for C for Catalan. I am also using something that you may know from formal languages. This A star is short for 1 plus A squared and so on. And then you take the star of this AC, and with those you can just solve the rest of the system of equations. So this is a shorthand representation in terms of, in this example, some known power series. But more generally, we can actually determine who are the we can determine who are the coefficients for every given monomial in the output. So if you give me a monomial, there's an algorithm that if you give me a monomial, I can compute the coefficient of that monomial. Even if that coefficient is infinity, I can detect that. That's a generalization of the Shmueli-Momake algorithm. Some things become undecidable. So for example, whether all coefficients are 0 or 1. You know why? You have to know something about context-free grammars. Because it's undecidable whether a context-free grammar is producing an ambiguous language. These are old stuff. Okay, I'm gonna. This one or? Yeah, maybe I should have drawn the graph. So notice there is an edge from A to B, an edge from A to C, an edge from C to B, an edge from B to D, and then there is an edge from D to D. That's the loop. Yeah, so V is the provenance of that loop. And the system says that V is equal to S plus V squared, V times V, because I'm using this bad way of talking about transitive closure. And that just gives you a more, I mean, I did it just to show you a more interesting power series. Okay, so I think we probably should cut it off here. I might just come back to these two slides at the beginning of the next segment, but I want to just mention, depending on your interests, there's been quite a bit of work on this. Let me just say, didn't have time to put this in the slides, but I recently attended the PhD defense of Jan Ramusa at École Normale Supérieure. And he used an even larger set of semirings, including some fascinating examples of semirings used for top K queries. So I will have all these references together with the slides posted on the website. And I guess we'll see you in half an hour, right? So I'm going to switch gears from what I would have called a more database-oriented presentation to a logic-oriented presentation. Of course, relational languages and first-order logic are very closely related. So I'm going to keep this here because I may have to come back and talk a little bit about absorption and absorptive polynomials. But before I switch to the logical perspective, I want to give you a small introduction to the issue of what I would call negative information. So you certainly observed that the languages that we used for declarative transformations through which we propagated provenance were the positive relational algebra, data log, which is plain positive data log. There were others that I didn't talk about, but they were all kept positive in various ways. And so naturally, one would like to ask, how about tracking negative information? And in particular, what if we want to examine the propagation of provenance through relational operations such as difference? Well, the main problem is that these operations being non-monotone, they cause, there's this expression, they throw a monkey wrench in the mechanism that we have developed so far. And from the beginning, this was actually a problem that was attacked in various ways. If you just stick to Boolean expressions, you can go beyond positive Boolean expressions and just consider Boolean expressions with negation. And that would, and in fact, this kind of provenance is perfectly acceptable for certain purposes. In particular, it's quite acceptable for probabilistic analysis based on where you start with provenance, which is a Boolean expression, which may have negation, and then you compute probabilities. And in fact, I remember the first time I talked to Serge Abitboul about this work on provenance. He said, well, wait a minute, this has been done by Mielinski and Lipski in 1984. And certainly he's right. If you look at conditional tables in the work of on incomplete databases, you will see that they are in fact annotated relations, and the annotations are relational, are Boolean expressions. And you can also deal with difference by negating some of those Boolean expressions, and it's perfectly good for those purposes. But for the more ambitious purposes that I described at the beginning of today, such as, for instance, dealing with trust, they are in fact limited, can do only so much. So understanding difference can be attacked by adding, just like we have a binary operation plus and a binary operation times for alternative and joint use of information, we could add a binary operation minus. There is this very nice work that was done primarily by the man in the back of the room, Floris Gertz, with Antonella Poggi and others later, of trying to axiomatize semirings with some operation that captures difference. In the Boolean case, difference is just and not. And for bags, you have what's called proper difference or monus. Monus comes from minus. And so they talked about something called M semirings. M stands for monus, which allows you to interpret the full relational algebra with difference, and which was then extended by Floris and others, including my former student Grigoris Karbounarakis, to deal with a language that's maybe of interest to some of you. You should know about this work, the language Sparkle for a, you know, semantic web. And there they have a variation of these mono-semirings. So the problem, with doing this is that it was not clear how to extend it to some other semirings of interest in a convenient way. And maybe the main problem is that while theoretically, algebraically, you can talk about a free M semiring nicely, there is a equational axiomatization of M semirings. The elements of this free M semiring are not as naturally easy to understand as the polynomials. They are equivalence classes of expressions in general, as in all equational algebraic theories. So this has not been very conducive because to progress, because the polynomials are much more persuasive and easier to implement and so on. Another approach that was inspired actually by Christoph Koch, and that was done by Yael Amsterdamer and Daniel Deutsch and yours truly, was to encode difference with aggregation, which has some interesting aspects and some other downsides. And then in another paper, we actually showed that all these different things, different ways of doing it, they give you different equational theories. Some equations are not satisfied by some of these approaches, and some are. And therefore, there are different algebraic optimizations. So I don't know, you should read these papers to see, if you are ever interested in this seriously, you should read these papers to see if you can get useful stuff out of them. So in some sense, it's still not clear how to track, was still not clear how to track negative information. And actual progress in a different direction in doing it, which has many positive aspects and some negative ones, which I will tell you about, was to switch to logic, and instead of talking about query answering, to talk about logical model checking, which is the logical perspective on the same thing. Query answering is same as model checking. This may come as a different way of thinking of things for some of you, but it is a very worthwhile thing to know in your research. And I strongly recommend that you understand the connection between database query languages and logics in some detail. It's just simple exercises that you can do. And they are all well explained in the Alice book. So some work that I did with Erich Gredl actually attacked logical model checking. And there we actually dealt with negation by duality, by going to negation normal form. And there were some interesting applications that I think made this while, which I'm about to tell you. And this is an older slide, but there's been quite a bit of work since then. So I'm going to get out of here, if I can. And okay, and start a different set of slides. This one is done with LaTeX in Beamer, and here it is. And I may go back to the other one with absorption later. Okay, so sorry, I forgot how to go to the beginning. Don't tell me. I prefer to remain forgotten. Okay, so now instead of looking at declarative programming as database query languages, we're going to look at first order logic. So first of all, the problem of model checking in first order logic is a problem that takes two arguments. One is a model, which is the A there, the Gothic A. So that's a first order model. And two, it takes a first order sentence, phi. So you can think of the finite first order model, but again, okay, so that's very important. We are not considering infinite models. We're considering finite models, which is why all the logicians who wanted to make good friends with computer scientists are doing finite model theory, which turned out for them to be fascinatingly difficult. Any logicians here? So now we have a finite model, which is like that input database, a structured collection of information. We have a sentence phi. And then if you ask, is this sentence true in that model? We have two answers, true or false. So instead of just doing that, which is the standard approach of logic, we want to do the provenance approach. In other words, I want to talk about the cost of it being true, the confidence, the number of witnesses, whatever that is. So if I can't, or if I want to talk about that, again, I want to do things like a quantitative approach, non-Boolean, and the approach that in finite model theory that takes first order sentences and does what's called grounding. It's not going to help with this quantitative approach. So let's see what it means to do provenance analysis for model checking. I should say that the database equivalent of logical model checking is query answering. You have a query, you have a tuple. Is that tuple in the answer? The question, is the tuple in the answer of the query, can be expressed as a model checking problem. So like I told you before, the kind of answers we can expect to using provenance is not just which information from the model is used in checking the sentence, but also why is the sentence true? And by why here we mean there might be alternative reasons, which is interesting, or even more vaguely expressed, but that's what the provenance polynomials do that you saw before. How is the information in the model used to check the truth of the sentence phi? And the framework uses commutative semirings, and this set of slides here repeats some of the stuff I told you, so I'm going to go very quickly through that. Commutative semiring, you know what it is. From the logical perspective, though, it is interesting to look at this. In a commutative semiring K, you use the zero to interpret false assertions. So false is unambiguous. And you use everything that's not zero to interpret true. So you can think of it as a nuanced interpretation of truth. Something can be more true than others. Yes, some more equal than others, yes, in the animal form. Okay, so you can think of it as an interpretation with shades of truth. And for a logician like Erich, this was kind of fascinated, and he fell into the trap, and he's doing a lot of work on that in recent years. So what here counts as the natural numbers semiring is going to be used for counting proof trees, so for counting different proofs in a finite model of that sentence. Then we have the tropical semiring, which you can use for cost. The Viterbi semiring we use for confidence. We have seen that. the commutative semiring used for access control. Okay, so the pub and conf and over here they are PCST. I'm not going to say much about this. Fuzzy semiring and the semiring for provenance that we have seen before. So all this is okay, except it's not appropriate for the provenance of negation. And from a logical perspective, there is an opportunity to take another path to attack that. And that's what will be the core of the second part of the tutorial. So here is what I'm going to talk about. I'll have an example with a simple graph and sentences about a simple digraph. And what do I mean by witness and what does it mean to count witnesses? We will interpret first of the final checking in an arbitrary commutative semiring instead of interpreting it as true or false. So that when you specialize the commutative semiring to the Booleans, you're going to get the standard interpretation. And we are going to have a way of recording abstract provenance, but instead of talking about polynomials as you saw them before, we're going to have something that we call, unhappily, dual indeterminate polynomials. It's a bit of a mouthful, but you'll see what it is. And that will allow us, interestingly, to provenance track assumptions in a multimodal manner, which means that we are going to track provenance not from a particular database, but from a family of databases with different assumptions, which allows us then to do backwards provenance and find which model satisfies which sentence. Okay? We call this reverse provenance analysis. And an example that we do there, confidence maximization. That is, here's a sentence. Among these models, find one that maximizes the confidence of checking the sentence. And reverse provenance analysis. So here there's be some interesting connection about the work that will be talked about by Jeff and I think others in this week about repairing wrong query answers, repairing queries, integrity constraint failures, and so on. Okay, so what's the, I promised you the running example. It's a digraph. The edge relation is E. And this is not such a useful graph theoretic property, but I'll just give it a name. We say that the vertex E is dominant if for any other vertex Y, there's an edge from X to Y, and there is no edge from Y to X. So X, this dominant vertex, has edges to all the other vertices, and there is no edge into that. So into that vertex, it is what's called a source in a digraph. So you can write in first of the logic, the sentence that you see there that says that X is dominant, and you, the predicate that says X is dominant, and you can write the sentence has no, that there is no dominant vertex, yeah, for all X, non-dominant of X. If we put this sentence, no dominant vertex, in negation normal form, which means to push negation all the way to the atomic predicates, we get this. You see it there. For all X, there exists a Y such that, so this is no vertex dominant. There exists a Y such that it's different from X, and well, there could be an edge from Y into X, or there could be no edge from X into Y. So this is the kind of stuff that if you ever try to do these kind of exercises in relational algebra, we just give them to students to drive them crazy in the database in the database course. This is just very hard to capture. But of course, first of the logic does it very natural. So the models of the sentence that I showed before look like this. They have a number of elements. Here are 3, A, B, C. And here are some edges. And don't try to read this, warning. This is what I call a proof tree. Okay, so this justifies a particular sentence, the sentence that there is no dominant vertex, and there's a proof tree there. And what you see on the leaves in boxes, those are the atomic information that this proof tree uses. So this proof tree uses the atomic information that say C is different from A, but that's trivial. We're going to assume this is one of those examples that provenance, you don't need to track it. It's just given to you. But we're going to track things like, well, there is an edge from B to A, one of the boxes. Things like there is no edge from B to C. So this we call a witness. And in a finite model, there are a number of witnesses for such a sentence. And in fact, there are finitely many such witnesses. So here is how we set it up. We begin with a fixed, this is very important, a fixed finite set of ground values. So I'm only like the model you saw before. I start with ABC, or I start with some other number, fixed finite number of values. So the development depends on that fixed finite number of values. And we have a relational vocabulary for databases. It's typical that we don't use function symbols, and instead we use relational symbols. Now, what's important here is that by fixing the finite set, we are essentially making an assumption that AI calls a closed world assumption. These are the only possible animals in this zoo, ABC. Yes? It is interesting, and it is something that that's worth working on, to extend some of these results to an open world in which you want to ask yourself, what does it mean to add new elements to the universe to make things true or false? But for what I'm showing you, it's a closed world assumption. I'm denoting by the facts of A all the ground relational atoms, the facts, like R of A. The negative facts, I'm denoting them by not R of A, neg facts. And the literals, as usual, are facts or negated facts. This is data log or logic programming terminology. So now, given a commutative semiring K, what is a K interpretation for our vocabulary and ground values? We start with a function that associates to every literal a value in the semiring. So this is where, these are like your assumptions that annotate tuples that you saw earlier. So here we have values that associate to facts and to negated facts some value in the semiring. If you want something to be true, you associate 0. So you associate 0. If you want something to be true, you associate non-zero, but it could be shades of truth. And you extend this mapping from literals to full first-order formula and sentences in the way in which you would expect. You probably don't need to spend too much time trying to decipher this notation, which is not friendly. But the important thing is that for equality and not equality, notice that the interpretation associates 0 or 1, whether true or false. For conjunction, it's multiplication in the semiring. For disjunction, it's addition in the semiring. For the basic values, you're just assuming, for the basic facts, R of X and not R of X, literals, that is, you're assuming, you associate whatever the original assumption pi is. Questions? Yes? Yes.
So I was just reading the last line,
Yeah.
and like usually, like one could say that the top symbols for like true is equal to the disjunction of a literal and its negation.
Yes.
Does that mean that somehow for each literal and its negation, the sum has to be the same?
No, it's no.
But then does it mean that that
it depends on.
is not a function over top? Because it doesn't.
Oh no. Okay. What you are saying is that does this interpretation preserve logical equivalence?
Yes.
That's what you're saying, right?
Yeah.
Okay. So, and the answer is nuanced. So please give me a chance to go forward. More interesting is that because we are in a finite model, we can interpret the quantifiers as sums, still finite sums, and products, still finite products. And finally, for negation normal form, we use negation normal form to interpret negation. So the interpretation of not phi, you put not phi in negation normal form, and then you interpret that. Which guarantees that you only use other clauses, because now the negation is only on the leaves, and you have defined that already. Okay, so one of the things we can prove right away is that it suffices to, you can either apply the rules as I described them, or you can actually put the formula in negation normal form and then compute the interpretation using the other rules but negation. Okay, so this is a first answer to your question. So consider now a finite model with a universe A and define an interpretation such that every literal is interpreted in the interpretation in the semiring of Boolean values, so that every literal is interpreted as true exactly when it is the literal, not the sentence. The literal is true in the model. Now, in what you saw before, I could have some crazy pi in which this is not the case. But if this is the case, then what you want is true. Because now it's easy to show that the interpretation of a sentence is true exactly when the sentence is made true in the model. So in particular, you can take the disjunction of phi and not phi, phi or not phi, yeah, and that's going to be true. But this relies on the assumption on what we make as basic assumptions about the literals. If those are crazy, then this is not true. But I will show you that crazy assumptions can be used for something later on in the, okay? All right. So maybe more interesting is the following result. So now you start with an interpretation in the semiring of natural numbers. And if the literal is true in the model, you interpret the literal as 1 and otherwise as 0. So now the interpretation of the entire sentence is a number, and it is exactly the number of model checking proof trees that witness it. So this is kind of the logical analog of bag semantics for databases to some extent. But there are enough differences that it's not clear that, so for example, and I know I should have done this work, but the relationship, for instance, with proper difference and so on, they're not, I don't understand them yet, didn't bother. I should have. Okay, so that's good, that's a good sanity check. I can use provenance interpretations in semirings to count the number of proof trees. I have also the equivalent of that diagram you saw at the beginning, but now it's not for a query language, some arbitrary, some query language, it's for first order logic, which is that if your interpretation commutes with a particular homomorphism between semirings, then this extends to full first order logic. Okay. So, all right, but now I have negation. So the idea that we had was to try to interpret both positive and negative information, building from the basic facts from the atoms up. So we are going to use provenance tokens like before, some set X to annotate the facts and a set X bar for negated facts. And the two sets are disjoint. Okay? And we also assume that there is a one-to-one correspondence between tokens, between the positive and the negative tokens, so that I can talk about a positive token P and denote with P bar its complementary token in X bar. And that's because I'm going to, most of the time, I'm going to use a token P and for a fact and a token P bar for the negative fact corresponding to that. I say most of the time, as you'll see that I can do some interesting things when I go beyond that. So how do we define our semiring of polynomials? So first consider the polynomials in which we use both kinds of indeterminates, both from X and from X bar, and take a quotient. So whenever you have somewhere in the polynomial PP bar, P times P bar, you replace that with 0 and the monomial goes away. Okay. In fact, it's not hard to see that this quotient is represented exactly by polynomials whose monomial contain no complementary tokens. So if there are complementary tokens P and P bar in the same monomial, the monomial is 0, goes away. And that's what we call the dual indeterminate polynomials, but that being a mouthful, I'm just going to call them dual polynomials. Dual indeterminate because they are indeterminates of positive and negative kind. Okay, and this has also a universality property, namely, if you have, for a commutative semiring K, some function that associates to the positive and negative tokens values such that P and P bar are mapped to values whose product is 0, then this extends uniquely to a semiring homomorphism into K. So that is, in a nutshell, another approach to dealing with negation that our goal was to consider, to take advantage of the fundamental symmetry between positive and negative facts logically. But at the same time, to do it in a nuanced manner. So things can be true at different levels of truth and or false. Okay, so let's see how we're doing this time. Okay, we have a question, and remind me, Diego, what time do I have to shut up?
12:45. You have to be kind of strict there because I have to.
Yes, what was the question? Yes.
Maybe it's completely unrelated and not even right. If I remember correctly, my answer quite accurate about the polygon. But like in a community semirings, you could have two non-zero elements that multiply to 0.
Yeah, divisors of 0. You can have that.
So does that mean?
No, that's bad. That's a bad semiring, huh?
Yeah. Okay. So So you are in a sense taking.
So I'm identifying those with 0.
Okay. But you, in a way, you would say, okay, what's interesting in practice to create the applications, you just don't take this kind of scenario.
Yeah. But you know, I mean, I'm trying to define it as general as I can, and so actually, all the semirings we work with, they're much nicer. But you have to be careful because here, if you work with polynomials without this identification, then you can have divisors of 0, which is not good.
Okay, but you would say from the logical perspective, it makes sense that then we just identify it.
Yes, so from the philosophical logical perspective, you should not assume both a fact and its negation. That's not the same as tertium non datur, right? That is, so assuming both a fact and this and its negation is what we call in America Trump logic. So, and not only in America. All right, so so let's do an interpretation that helps with provenance. So here is what my assumptions. I can choose, for instance, to interpret the presence of an item in the model with some literal t, with some token t, and I can choose to interpret the absence of something like here with p bar. Yeah. In the picture that you see there, the solid arrows are for the facts that are present, and the dashed arrows are for the stating the absence. Okay. So using such a provenance tracking interpretation, we can compute for a sentence. Remember that sentence I had at the beginning that said there is no dominant vertex? Well, let's think about it. So there is no dominant vertex means that A is not dominant, B is not dominant, C is not dominant. And why is A not dominant? Because there is an edge from B, or because there's no edge from A to B, and so on. So you can capture all of these. That's the sentence, if you don't remember it, but here it is. You can capture all of these as this polynomial. So I wrote it first as a product. So these three factors of this product correspond to A not dominant, B not dominant, C not dominant. Well, then you can multiply it out. There may be some simplifications, although not in this particular case, but when you multiply P and P bar, eventually some things disappear. So you get this. So what do I have here? The number of witnesses can also be told by this polynomial. We just make everything 1, everything that's true 1. So then the number of witnesses is 8. There are 8 monomials here. And each of these monomials corresponds to one of the proof trees that witness the fact that there are no dominant vertices. Okay. You can also use the universality property I showed you before that extends to mapping to these dual polynomials and calculate confidence by evaluating this polynomial in the Viterbi semiring. So assume that RS and T are there with confidence 3/4 and P bar Q bar with 2/3, blah, blah, blah. You just maximum that's confidence 9/16. You can or cannot interpret this multiplication as independence. Here it is easy to do that because, but the assumption is that each of the presence and absence of edges in the model is independent of each other, mutually independent. Okay. Whether that makes sense in our application, who knows? Hey, what did I do? Diego did something very careful there. Why did I have to touch that? Okay. All right, so good. Now, I told you that I can also consider some bizarre assumptions that may actually appear to be contradictory, but that's because I'm not considering specifically one model, but I'm interested in multiple models. And for example, I'm interested in, here is a sentence, among these models, how can I choose one that might make it true and also with maximum confidence, for instance. So multimodal provenance assumptions are these things. So we say that an interpretation into dual polynomials is model compatible if for every fact R, you have one of the following three wholes, not all three, just one of them because they are mutually exclusive. You can interpret the fact as X and the negation as X bar, or you can interpret the fact as 0 and the negation as 1, or you can interpret the fact as 1 and the negation as 0. So the interesting thing is that in alternative 1, I'm allowing for both the fact being true and the fact being false, and I'm going to decide later which one it is, depending on what results I want to get. So if you have such an interpretation, you can actually define the set of models that are compatible with this. And namely, all you need is models in which if, yes? Which one is different from 0? No, but X is an indeterminate. So I'm not yet interpreting X or X bar as anything. I'm allowing for the possibility of choosing one or the other by using abstract names for them. Yeah, but also it's possible that you want, so alternatives 2 and 3 are if you do not want to track anything. So you choose not to track the presence or the absence of a particular element of the model. And alternative 2 means that the element of the model is absent. Alternative 3 is that the element of the model is present. Alternative 1 is you don't know which one, but you're going to determine it in a moment. Okay? That's why it's multimodal. So there's not a single model. So we have to allow for the possibility of having multiple models that will satisfy the sentence. Okay, so the set mod P is the set of all models in which, well, if we actually insist that a particular literal, positive or negative, is 1, then it has to be satisfied in the model. So it's like basic compatibility. But if the literal is interpreted as a value, as one of these indeterminates, either can happen. So as an example of a multimodal assumptions, you may have noticed that the arrows here have turned from solid to dashed to dotted. So the dotted ones can be either solid or dashed. I don't know if it's such a great choice, but that's the meaning. Notice that the dotted arrows are actually labeled with both a positive token and a negative token. That's what I mean, that they can end up being both true or false, T and T bar. Okay? There's also a whole bunch of things here which are not even drawn on the picture because they are 0 or 1. Yes? So the model that you use, the P that you have here is model compatible. And let us compute in this interpretation The polynomial that corresponds to the sentence, there is no dominant vertex. Here it is, the polynomial. It's a product of three simple ones, and I could multiply. This is a situation when you multiply, you have, for example, p times p bar. That's going to be 0. But I'm not going to multiply it because the resulting polynomial has 34 monomials, and I'm going to spare you the sight of that. But the point is that there are 34 distinct proof trees that witness the model checking, but not in a single model, but in any of these models in mod P, in some of these models in mod P. Also, it's interesting to look at the negation of that. So the negation of there is no dominant vertex is there exists a dominant vertex because it's a simpler polynomial, and it's this one, PRT bar plus P bar QS bar. And this one has two monomials. And here it's very interesting is that the two monomials in this polynomial do not correspond to a proof tree in a single model, but in two different models. They can't be both true in the same model. Okay. So why does this all work? We have a little result here that says that this provenance polynomial describes all the proof trees that verify phi using premises from these literals. And if you look at the monomial in these polynomials, it may have a coefficient m. That means that there are m distinct proof trees. It will have exponents, m1, mk. So for example, mi says that the literal xi, now xi could be a positive or a negative literal, is used mi times. So my point, one of the points I'm making is with this approach, we can also track negative information and negative facts that are used multiple times. Okay. And as a corollary of that, we say that the sentence, we can show that the sentence is satisfiable in one of these models if and only if its polynomial is different from 0, and valid in all of these models if and only if the polynomial of the negation is 0. So you're going to start screaming now. No? Nobody? Anybody says Trachtenbro's theorem? Huh? Okay, so we do know that validity is not, so this is not for one model, it's for a class of models. But we know from Trachtenbro's theorem that, that validity is undecidable for all finite models, except this is not all finite models. Mod P is only the models built with a fixed universe. The universe was fixed at the beginning and therefore it's decidable. I mean, it's in fact NP complete. Okay. So this special kind of satisfiability validity is decidable with the polynomials, but because it's restricted to this. And I can now take an interpretation in the Viterbi semiring by mapping the provenance tokens, all the positive ones to 2/3, the negative to 3/4, for example. And I can find a model that maximizes the interpretation in the Viterbi semiring, for example, for the simpler sentence, so we don't have to understand 34 monomials, the one with there exists a dominant vertex. And there are two candidates, so you choose the one that makes maximizes this, so as 1/3. So the solution is a model that makes through the literals from PRT bar You can go there and you see that means you need an edge, two edges to be there in the graph corresponding to P and R, and the edge that corresponds to T bar not to be there. Okay. All right, so now some stuff about missing query answers. Suppose that I can use, what I want to show is I can use the same framework to talk about provenance or justifications for the fact that a particular tuple is not in the answer of a query. So consider the query dominant of X. So now this one is a predicate. And its answer is which of these vertices are dominant. And for example, B is dominant. And the provenance of dominant of B is P bar Q S bar T. So you want to have those in. And now the question you might ask is, why is A not an answer? And why is A not an answer cannot be answered usefully with computing the provenance of dominant of A. Because it's zero, because A is not an answer. What you want to find out is the provenance of not dominant of A. So you compute the provenance of not dominant of A, which is this sentence. You get P bar plus T. So you can interpret this as both explanations, and in a moment I'll show you as repairs. So the explanations, there's an alternative in the explanations. It's P bar plus T. So one possible cause that A is not dominant is the absence of the edge E of AB. An alternative cause is the presence of the edge E of BA. And this approach is complete. These are all the possible reasons why, all possible explanation. It also gives you an approach to repairing, which means you want to make, so in order to make dominant A true, you want to make not dominant A false. So you just want to solve the equation P bar plus T equals 0. And that means P bar should be 0 and T equals 0, both. And that means it tells you which edge to insert and which edge to delete. So that's a possible repair. So negative token set to 0, that means you insert a fact. Positive token set to 0, that means you delete a fact. And this is how we can approach missing query answers. Interestingly, because this is something that deals with full first order logic, we can also find out why whatever integrity constraints we can express in first order logic fail in a model. So here's an example, again, in terms of dominance and so on. So obviously that's not maybe of interest to integrity constraints that you have. But in terms of, let's say we have an integrity constraint that says at least one vertex is dominant and it's failing. And you want to know why is this integrity constraint failing? Well, again, it has, what you want to do is look at the provenance of not of the negation of this integrity constraint, which I calculated here. And this polynomial with 8 monomials gives you 8 alternative explanations. Now, if you analyze these, you will find that 4 of them are redundant. Who are redundant? Well, look at here. You see P bar Q bar and P bar Q bar R. So P bar Q bar R is redundant because it is implied by P bar Q bar. This has something to do with absorption, which I don't think I'll have time to talk about much. But P bar Q bar is one possible cause. An alternative cause could be P bar S, and there are 2 more causes. So TQ bar and TS. So these last 4 are redundant, but the first 4, let's call them minimal causes, are actually giving you explanations of why that fails. And you can actually look at the repairs as a tree. So you want this polynomial to be 0, so that means making one of the 4 binomials to be 0. The third one cannot be because it's 1 plus r. And the other ones, it's here. The other ones are, to make it 0, it's P0, you must have both P0, 0 and T0. So that gives you the repairs. So each solution corresponds to a different repair. And we can prove that all minimal repairs, but that is repairs who do not imply other repairs that are in the polynomial, can be represented as solutions given by the AND/OR tree. And while there are, in general, exponentially many minimal repairs, the tree is of polynomial size. So it could be analyzed separately, potentially for efficient algorithms for some question or other. We also found that some non-minimal solutions may also appear in the tree. And we're not quite sure how to get rid of those, but still the tree is of polynomial size in data complexity. So if you have multiple repairs, can this framework help you to choose among multiple repairs? And the answer is the following. Let's say, so remember the integrity constraint that we had, and let's compute now the provenance not of the negation. So we computed the provenance of the negation of the integrity constraint in order to find explanations / repairs. Now let's compute the provenance of the integrity constraint itself. Here it is. And then apply each of the repairs that you obtained from the tree. And the repairs are going to give you these 2 corresponding monomials. So the integrity constraint has now this provenance in the case of each of the repairs. So it has the provenance PRT bar in the case of the first repair and P bar QS bar T in the case of the second repair. And if you interpret these polynomials in a cost semiring, so here are some assumptions pulled out of a hat, that the facts cost things like 10 bitcoins, 5 bitcoins, whatever. And then you want to compare the cost of PRT bar and P bar Q as bar T. Well, one turns out to be 45 and one turns out to be 50. So you can choose the one with the minimum cost, for example. Or you can choose the one with the maximum confidence, like we saw something earlier done this way. My point in this very, very fast introduction is to make you interested in possibly using this framework of these dual polynomials to capture provenance for situations in which negation is used, and to see if they can apply to other kind of situations. One of the things I have not said anything about is what happens with data log when we add negation. So what happens with if you are familiar with this, with the theory there, an extension of data log that deals with negation in a satisfactory manner is called stratified data log. So when you have stratified data log, you have least fixed points that are in strata, and then from one stratum to the other, you negate the answer. Now, if you try to deal with all of them at the same time, you can embed stratified data log in a logical framework, in a logic. This logic is obviously not first-order logic, but it has to deal with some kind of least fixed point. And because of the negation, it has to also deal with the dual of least fixed point, and that's greatest fixed point. And there is a logic that does that. It's called LFP, which is a weird name because it means least fixed point logic, but it has both least and greatest fixed point. So I don't know, I call it fixed point logic. So this is first order fixed point logic that works like so. So if you recall, I made some fuss in the earlier session this morning that if we try to extend the semantics of data log to bags, we may end up having to iterate infinitely many times to get an answer, but we can stop after, just like in the pumping lemma, we can stop after finitely many times and determine, okay, this is going to be infinite, right? And when you do provenance, it's even more abstract than that. In the parlance of fixed point logic, this is called the closure ordinal. So the closure ordinal for set semantics for data log is some finite number. This is determined by the model. The closure ordinal in general for bag semantics for data log is omega. That is, you need to iterate, but only count up to the first ordinal. It turns out, and I showed you in the morning how to extend this to something called omega continuous semirings, blah, blah, blah. But the price to do that was that instead of Provenance polynomials, we needed to use formal power series. Now, in recent work with Erich Rehl, Matthias Naff, and initially also Katrin Dannert, we have actually tried to extend this to fixed point logic. So let me just give you a hint of how that works. So what is this LFP, fixed point logic? So it has both least fixed points and greatest fixed points operators, and they alternate arbitrarily. So you can take the least fixed point of a greatest fixed point of a least fixed point, and so on. What is that? Well, you have to add to your fixed point logic, to your first order logic, this rather not easy to swallow construct. So LFP of R of X dot phi, this takes the fixed point of an equation, R is equal to phi of R. The X are just some free variables. And the formula phi in both cases must be such that R occurs, this variable, this higher order variable that you take the fixed point for, must occur positively in the formula. What does positively mean? It must occur under an even number of negations. So that's decidable. You could, in general, consider a logic in which you don't necessarily count a number of negations, but you're just saying the function must be, the formula must be monotone in R. The problem is that's undecidable. But if you want a decidable syntax, which I don't know, I do. If you want a decidable syntax, then of course, it turns out you can be happy with just occurring under finitely, evenly many negations. And then you have a monotone function, and you have to work over, in general, over something called a complete lattice. And then there is a theorem by Knaster and Tarski that guarantees that every monotone function has both a least fixed point and a greatest fixed point. And that's the semantics foundation of fixed point logic. All right, so far so good. But what to do with provenance? Why is this attractive to us? Well, because like I said, stratified data log is easily embeddable in this, but moreover, verification logics, which may not be your, on your first menu, but verification logics such as linear temporal logic, branching temporal logics like CTL, CTL star, the new calculus, they can all be embedded in fixed point logic. And all of them, actually, in all of them, it makes sense to consider provenance issues. I mean, just because the verification people did not, doesn't mean that we should not eventually try to consider provenance issues in verification logic. So it is of interest to extend provenance, this provenance framework to fixed point logic. Again, briefly, I'm waving my hands here. The technicalities are too complicated to hope for me to explain. A major difficulty is caused by the need to give dual semantics to greatest fixed points, dual to LFP. And some of you may know that you can eliminate the greatest fixed point in favor of the least fixed point using something called the stage comparison theorem. But that's, before you ask about it, it's a bad idea. First of all, it explodes the size of the formula, and all the intuitive understanding of provenance, which I tried hard since this morning to make a fuss about, just kind of goes away. So what worked, though, is that we considered fully chain-complete semirings. So these are semirings that do not just have omega, not just the chains of ordinal omega have a least upper bound, but the chains, every chain of an arbitrary cardinality has a least upper bound and a greatest lower bound. So that's fully chain complete. And moreover, if these chains also, these least upper bounds and greatest lower bounds also commute with the operations of the semiring, then we have a fully chain continuous semiring. Trouble is that the closure ordinal is not omega anymore. And instead of using iterations up to omega, which is what we do, so there is this simpler case of the Knaster-Tarski theorem called the Clini fixed point theorem, in which you do only iterations up to omega, but you have to assume more about the function than monotonicity. So we cannot assume more than monotonicity, but you have to then use not just recursion up to omega, but transfinite recursion. So when you get to ordinals beyond omega, you have to take limits. And this works fine in the framework, but is not particularly informative. It does work with those formal power series, but not as informative as we were hoping for. What we have discovered, however, is that if we stick to polynomials which are absorptive, so what's absorption is this condition, a plus ab is a. Polynomials which are absorptive, then all of a sudden, and semirings which are absorptive, all of a sudden things are much friendlier. We just have to extend the absorptive polynomial. Somebody asked me about the infinite exponents. With exponents which are infinite, which means from a provenance perspective that you can use a fact infinitely many times in a derivation. Okay, so that's all I give you. There's a paper about this that appeared in Logic Colloquium, but it's also on Archive. Please feel free to contact me. I should have put my email there. Val at either seas or cis.upenn.edu. This tells you how old you are. Actually, Susan's address at Penn is Susan at you can also reach me by val@upenn.edu. Susan is Susan at upenn.edu. And Peter used to be Peter at upenn.edu when he was at Penn. So that tells you how ancient you are. Because that means you were there when there were so few people that you could actually use your first name as your as your identifier.
How uncommon is your brother?
That's right. Okay, so I just wanted to show some list of people that I owe much to. So this work originally started with a PODS 07 paper with my two students, TJ Green and Grigoris Karpounarakis. They had interesting careers in several places, including logic blocks. Anybody here knows what logic blocks is? Yeah. But somehow TJ is now at Amazon Web Services. And in Grigoris, I think I don't know. Okay. Zach Ives, my colleague at Penn, was instrumental in asking me questions like, what about trust? We don't know how to deal. If we use lineage, as in Jennifer Widdom's approach, we cannot deal with trust. And well, you saw that we can. I also worked with Nate Foster, who's a professor at Cornell, on XML, and I had some excellent collaborations with Yael Amsterdamer and Daniel Deutsch, who were postdocs with me. Actually, Yael was a pre-doc. She came before her PhD, but she did work worth many postdocs together. Tova Milo from Tel Aviv University, who is their advisor, Sudeepa Roy, who is now at Duke University, Yuval Moskovich. And then recent work with Erich Gredl, like I told you, and Matthias Naaf. And well, Peter actually got me interested in this provenance in the first place. So I'm just gonna stop here and take your questions.